So what diagram we have seen? Now you can see instead of diode, only resistor I have taken. So that resistor we can represent RE. RE means across the emitter is connected. Also you can take RE is due to common emitter configuration you have taken. RE you can write. Similarly, here you can see RE is equal to this one. So any confusion here in the diagram? Step by step, it is represented here. Now coming to this RE, this dynamic resistance, also you have studied the dynamic resistance of a diode. So if you have remembered, that is 26 millivolt divided by DC current, which is flowing through the diode. So here you can see what is the current is flowing through the diode. This is emitter current. But remember, that current is DC current. So how to find out the DC current? When you are taking DC biasing. So that's why you can see here it is written that resistance value of this RE we can write, we can calculate 26 millivolt divided by IE. And this IE is not DC emitter current, not this small e. Are you getting me? Hello? Am I audible to everyone?
Sir, can you repeat why you are taking capital E1 instead of small e1?
So this is, you can see when I am taking a AC source, VI, so at that time I am taking input, that emitter current will be small IE. But earlier DC biasing, what you are taking? For example, for this configuration, you are taking VCC supply voltage. Now you are taking this emitter. Here, for example, you are taking. Now this transistor here, transistor is here. So if I'm taking this transistor, if I'm taking this current source, now this is point, now this is your diode. Okay. Okay. So due to this DC supply voltage, now you can see what if it is connected to same DC voltage, or I am giving, because already you have know, because I am connecting with here, I can connect here supply voltage VCC. Okay. So due to this DC supply voltage, what is the current you are getting here? So that will be emitter current capital I. This is your IC and this is your IB. Are you getting me? So that DC current, if you have taken, or also you can see, this is a network when diode is connected. So what current is flowing through the diode? So that DC current you have to consider. In some question, it may be given to you, or either you have to find out the DC current. How to correct DC current? So DC biasing you take, first you calculate the IB values, then you can find out IE values. So the which is equal to beta plus 1 IB. And this IB or capital B means whatever earlier biasing method we have followed, if any biasing method you are following, so that during DC biasing, what IB, IC, IE you are getting, once you got IE, that IE will help you to calculate this RE value. So that RE value, how to get it? So 26 millivolt divided by IE.
Yes, sir, got it. Thank you.
So that's why it is written here. This resistance value RE you can calculate 26 millivolt divided by IE. Capital you can see here. This is DC emitter current. Now, if I am taking this transistor, now you can see this is in blue box. Now already we have seen in this common emitter configuration, we have not used any resistors like RB, RC, RE is not connected till now. So now, if only this transistor I am taking a blue blocks, now this is a two-port network. Okay. So in this two-port network, if I am giving the supply voltage VI, so we have to find out what is input impedance, what is output impedance, and what is my current gain. So what we have done earlier, you have remembered in earlier case also I have told if I am taking a two-port network. So now we have to find out input impedance, output impedance, and what is the gain of this transistor. So gain of the transistor you know because IE is equal to, sorry, IC is equal to, beta is equal to IC by IB. So it will be beta values. Now corresponding input impedance and output impedance we have to find out. So input impedance you can see how to calculate. We'll see the step by step for common emitter configuration. Now the input impedance first you have to calculate, which is Zin. So Zin you can see you are looking from this here. So which is depending upon what is my input voltage Vi. So now, so your input impedance, I can write what is my input voltage and what is my input current. So Vi by Ii, and Ii is equal to nothing but this is your base current. So I can write Vi is equal to, and also Ii is equal to Ib, and you can see this input voltage, what is the voltage here. So this voltage I can take, what is the voltage across base to emitter. So this is base emitter. So that's why I can write what is the voltage here? I can write VB. And VB is voltage across your resistance only. Now the level of RE still is determined by the DC current IE. So using the Ohm's law here, we can write here Vi is equal to VB, which is, you can see how to calculate VB. Now what is the current is flowing RE. So the voltage, so I can write Vi VB is equal to IE into RE. Okay. Now, if I put these values here, input impedance, so I can write here, instead of IE, I can write beta IVRE, because IE is equal to here, IE is equal to beta plus 1 IB, which is approximately beta into IB. So that's what is put here. Now, this equation Z input impedance we can write VB by IB. So now I can put beta IBRE divided by IB, so which is equal to beta RE. So now here input impedance you can see which is equal to your beta RE value. Clear?
Yes, sir.
So generally, if you see practically, few in common emitter configuration, if you are taking input impedance, which is approximately in between kilo ohm range, so it is 6 to 7 kilo ohm. For the it is this data is given 5-10 years back. Now it may be because it depends upon device developed by the company. And this input impedance, based upon that, they are taking, but it will be provided in the data set, because what is RE value or beta value, based upon that, you can decide what should be impedance value. This is the approach to calculate the input impedance in a common emitter configuration. Now, similarly, what will be the output impedance? Anyone can tell me? What should be the output impedance of the transistor? Or how to find out output impedance?
VC by IC.
VC by?
IC output current.
VC, okay, VC by IC, because this current is IC, because this is, you can see across this one. But this characteristic you can get it also from the output characteristic of your transistor. So if you remember, the output characteristic is like this one. No? Okay. So what you told, it is also right, because you have plotted between IC versus VC. So now if you take this curve, now if I am taking the resistance value or output impedance or resistance, So here this resistance, you can see change in voltage by change in current. And you can see it is a constant. So change in voltage will be 0, but change in current will be there. So if you see this in resistance will be change in VC divided by change in IC. So change in VC means also here. So change in VC will be there. For example, I'm taking this voltage, and change in current I'm taking this one. So change in current will be 0. So now plus VC divided by 0. So what will be the value? So it is approximately infinite. So your output resistance of your transistor will be infinite, and here you can see output impedance which is equal to your R0. So then output impedance also infinite. So once I'm going to that part. So here same thing I'm showing you here. So what I told. So it is characteristic of common emitter configuration. This plot is IC versus VC. So if I'm taking for any input current, so if I want to calculate my resistance here, so this resistance I have to find out. So this resistance I have to find out change in VC. So R0 is equal to change in VC by change in IC. But change in IC and VC, you can see you are getting a very higher value due to this behavior for output characteristic. So which is very high value. And here this resistance and output impedance, you can see it is same. So here you can see Z0 value is very high, so 40 to 50 kilo ohm. Ideally you can take infinite, but practically it is very high value, 40 to 50 kilo ohm just taken. And the applied signal is set to 0, and the current IC 0 milliampere. So the output impedance will be Z0 R0, which will be approximately infinite for an ideal case. So this is all about input and output impedance for a common emitter configuration. Any queries? If something is not clear to anyone, please let me know. Okay, so similarly, you have to go for, now same thing it is represented here. We have to derive the voltage gain and current gain. So whatever transistor earlier it has shown to you, so this is in blue box only, same thing if you see 3 point. So here, so you have taken, this is current source. So this is your RE. Okay. Okay. So VCE, sorry, small letter we have to take C and B. So this is inside this. Now you can see here we have calculated input impedance beta RE and output impedance is infinite. Now input current II is equal to IB, and here you can see IC is coming to this one. Now in this circuit, if I'm using voltage gain, you have to calculate. So you have to take a resistor, load resistor. So load resistor is connected here. So voltage gain means output voltage divided by input voltage. So now if I'm taking this output voltage which is across the load resistor, now here you can see this current I0 will be this one. Output current which is flowing to this RL. Or I can take, okay, this is already I have taken 0, so I can take, this is I dash 0. So now this is, you can see this is IC and this is I0, and the relation between IC and I0 will be opposite to each other. Are you getting me? Because this current which is flowing through the RL, the direction will be like this. And IC direction is towards this one. So if you see, magnitude will be same, but out of phase. So that's why whenever I'm calculating the voltage here, so voltage I can write I0 dash into RL. And I0 dash is equal to I0 minus I0. So that's why V0 is equal to minus I0 RL. And I0 is equal to beta IB. So I can write here IC into RL, I can write minus beta IB RL. I hope all is clear this point because many people are confused why minus sign is there. Is it clear to everyone?
Sir, can you again explain why I dash 0 is moving in
Okay.
that direction?
So, okay. Now, what will be the output voltage? Here, V0, for example, output voltage I am taking across RL. So this current you can see, this is because if I'm taking, you can see plus and minus sign here. So current will flow from this point to this point. Now, for example, I am taking this symbol is current I0 dash. So now voltage will be I0 dash into RL. Your output voltage will be I0 dash into RL. Is it clear?
Yes.
Now, if because in transistor current known to you because IC is known to you. So now the relation between I0 dash and IC, what is that? Because this is opposite to phase, you can see this is opposite to this is the current is flowing this direction and current is flowing this direction. If I'm using KCL here at this node, so then I dash 0 is equal to minus IC. So same thing I kept it here. So V0 is equal to minus IC into RL. Now this IC is equal to beta IB because this IC is equal to beta IB. So now we are putting IC is equal to beta IB. Clear?
Yes, sir.
Yes, sir.
Now, once you got output voltage and also you not input voltage. So input voltage is equal to beta RE because input voltage is equal to VI. So VI is equal to IB into beta RE because input voltage will be IB into beta RE. So voltage gain will be V0 by VI. So same thing we have written. So input voltage VI is equal to I into ZI and already you derived Zeta is equal to beta RE. So we can write beta IB RE. Now voltage gain will be V0 by VI. So voltage gain will be V0 by VI. So now we can write this equation minus beta IB RL divided by beta IB RE. So beta IB will be cancelled. So your output voltage gain is equal to minus RL by RE. So can you tell me what is the significance of minus sign here? Anyone? Hello? So simple meaning is you can see because whatever, for example, I am taking input because this is voltage gain. Na? So for example, I am taking input is equal to this one. So this is my VI. Okay. Now at the output, what you will get? Voltage gain will be amplified. Now it will be amplified like this. And this is your V0 and V0 is equal to AV into VI. Okay, but minus sign signifies, so it is out of 180-degree phase. So what will be there? So this input will be start from here only. Okay, so because here this amplification will be like this. Okay, so this is your input and this is your output. So this minus sign signifies the input output phase change will be 180-degree. Clear? Now current gain also similarly, current gain will be what is output current by input current. Output current already you know that is beta IB, input current is IB. So current gain will be beta only. So now in common emitter configuration if you are taking, without considering your other resistors like RC, RE, RB, so if I'm taking the simple configuration here, voltage gain will be depending upon load resistance divided by dynamic resistance. And current gain will be beta. Now very important point here, this R0 already taken very high value infinite here. Because input impedance, output impedance is infinite. It is clear to everyone or any queries here? Any point, any particular thing, you have any queries, please ask.
Once again say, sir, output 180 degree out of phase. How?
So this minus sign signifies that there is a phase change. If you see how it is phase change, you can see if I'm taking, for example, you are taking sine theta, and I'm writing sine 180 minus theta. What is the value? Because this is sine wave, no?
Okay, sir, understood.
So that's why whatever, because if you're taking this signal like this, so the input and output, there will be phase change. You can see you are starting from here now. So this is 0 degree. Now this is, you can see now you are starting from here only. This is opposite phase. So 180 degree phase shift is there. And voltage gain, if you see magnitude point of view, this magnitude will be voltage gain into what is your input voltage. So
Sir,
later
what
on you
is
can
the
see some devices like no phase change will be there. So now if you want to, for example, if you want to take any circuit where amplification is required, but there is a phase difference would be 180 degree. So then this type of configuration you can consider. Now, for example, I need a 360 degree phase shift. So then you can see two-stage amplifiers. Two-stage amplifier you are taking, amplification gain will be accordingly it will be multiplied, and your phase will be same phase, whatever phase you are giving, the output will be same phase. Because in second phase also there will be a phase inversion. So 180 degree, 180 degree is equal to 360 degree. So it will be a replica of your input signal, but with a magnitude will be AV1 into AV2 into your input. Okay, any other queries anybody have?
Sir, what is the significance of RO being infinite output resistance?
Because here you can see, if I'm not here, this resistance, what we have taken, this resistance we have derived previously in common emitter configuration. If I'm taking ideal value, it will be infinite. Or if you, that's what is given here. So, or if you're taking, you can take a very higher value. Higher value means it is already, it is 40 kilo ohm or 50 kilo ohm you can consider. So that's why this RL value, because you need a very high voltage gain. So this RL I have to take more. Why it is take to more? Already I told this impedance and this impedance should be matched. So if you see, I feel I need a very high voltage gain. So similarly, I have to take a very high load resistance value. I
So,
hope I
sir,
can.
it is a
Tell me.
finite value just because it is very high, so we consider it as
Huh.
infinite.
But that's why I told the ideal case. You can see here, previous diagram, I hope it is because here you can see some circuit you can see in common emitter configuration. Ideal means I have told you like this, na? So now if you see this
Yes, sir.
voltage may vary, but current will be very small, na? So this will be zero. So now if I'm taking change in voltage by change in current, because this is a constant, you can see for amplifier, I need this type of, in active region, it should be look like this. So then this change in IC current will be minimum or zero. So that's why ideally it should be infinite. But if you see, if I'm getting this behavior, so still also you can see this change in current will be very small because it is milliampere and it is in volt. So automatically you will get very higher value in kilo ohm because this is voltage divided by milliampere. Milli means 10 to the minus 3. So it will go to the top side. So it will be in kilo ohm ratio. Okay, so based upon this, it will be more clear to you. You can take in one example. So here, so RE model for common emitter transistor configuration. Okay, same. If you see earlier circuit and this circuit, what is the difference? Anyone can tell me, or both are same? Okay, I'm going to that point, and it both are same. How it is same? Here I'm drawing. Okay. Now you have seen, now this is the input network you have seen. Now if I'm taking, now this is, you can see emitter is common. So I'm taking emitter this line. Okay. Now input is, now I'm taking input IB. Now this is my base. Okay. And this is my collector. So I am taking, this is the line. Okay. Now in between base, collector, emitter, because emitter I can take two lines. For example, I can take emitter, I can split it, or I can take it one line. Okay. Now you can see in between base and emitter, resistor is there. So resistance will be there. So I can writing beta because input resistance. Okay. Similarly, across collector and emitter, what is there? One current source is there. So current source I can write like this is your current source, beta IB. So this circuit and this circuit are same or different? Anyone?
Same.
So same thing there also, because here it is splitted like two port I told, this is your input. So I can write this is my ZI and this is my Z0. So same circuit, this circuit we can represent also in same approach. So in that slide I have shown directly there.
So can you please explain it once again?
Okay. So here you can see for a transistor, three terminals are there. So already you see emitter is common. So I have taken emitter line here. Now I can take base is one line. So base and collector I am taking one line. Okay. Now here you can see what is the resistance value. You can see it is connected from base to emitter input impedance. So this input impedance Z in I can write here, which is beta R. So I can write. Now in the output you can see this is the current source. So I can write current source you can see which is, you can write here. Beta IB or IC, we can, it is in between collector to emitter. You can see this is output impedance you have taken. No? So now we can see this is the current source here.
Okay, sir.
That I am going to this diagram and I am making what other changes are there. It will be more clear to you. Okay. So beta R is given input impedance. This is correct. Now what I have not shown you R0, because when R0 is infinite, so R0 you can not consider. Now previous cases R0 you have not considered because you have taken R0 is infinite. Now for example, as you told, if I am taking a finite value, so we can also represent one R0 here. Is it clear? So same diagram here, input impedance, same thing what I have derived, input impedance beta R and output impedance is equal to R0. So if you are taking infinite, then this line will be R0, you have to make it open. Because infinite, how to represent? You have to make it open. Okay, so if you are taking finite value, then I can put it R0 here. Now, based upon this, what we discussed, can you calculate these values? Beta is 120, I is equal to 3.2 milliampere. This IE you can see, this is DC current, so don't confuse. If sometime it is not given, then you have to do DC analysis and you have to find it out. In some question, if directly DC current is given, then you can utilize. So here you have to find out the voltage gain and current gain. So already this earlier equation you can utilize what you derived. Now you can find out the voltage gain and current gain. Simple thing, because your voltage gain already you know RL by RE. So here only thing is not known to you, your RE value. So RE value you have to find it out. So RE value is 26 millivolt by IE. So you can find out 26 millivolt by IE, which is equal to 26 millivolt divided by 3.2 milliampere. So it will be 8.125 ohm. So this is your RE value. Now input impedance will be beta RE. So beta RE will be 975 ohm. Beta value already given 120, and you can use that value 120, then you can find it out. Now voltage gain already you derived RL by RE. So RL already given 2 kilo ohm. So 2 kilo ohm divided by 975 ohm. So RL will be minus 246.15. So 2 kilo ohm, some mistake is there maybe, no, this is right, because RL by RE, which is equal to minus 246.15. So whatever input you are giving, output will be 246 times, but there will be a phase change of 180 degree. So current gain will be beta, and beta already given 120. So same simple thing what you have done previously, same thing is you have to calculate. I hope everything is clear, or any queries? Is it clear to everyone? Am I audible?
Yes, sir.
Yes, sir. Okay. Now this is similarly you can go for common base configuration also. What process we followed for common emitter configuration, you can follow same thing for common base configuration. It is also in your book, but as common emitter configuration is popularly used, I have shown it. Common base also I have 2-3 slides I kept behind this. I can forward to that, but same process you can refer it. Only changes you will see here. Input impedance is equal to beta RE. Their input impedance will be only RE. So this changes what you derived here. Same process you follow. So input impedance will be only RE, but here it is beta RE. So this is the only changes. And you can see from this amplifier design, already I told input impedance should be higher value compared to, if you see common base, input impedance is only RE, but in common emitter, it is beta RE. So that's why your emitter, common emitter configurations are used for amplifier. So now in BJT, then we'll go FET, then MOSFET, then we'll go for op-amp. So in each case, you can see input impedance we are increasing. So remember, this is a basic point. So in these devices, researchers are trying to provide more input impedance for a better amplification. Okay, so that you can see in common base configuration, and you can see their input impedance in common emitter application, common emitter configuration, see the input impedance. Now coming to a stabilization part, already I told in a transistor, stabilization is very important factor, and which you calculate, already I told, change in output current divided by change in leakage current. So similarly, stability, if you see, you can calculate using 3 approaches. So one is in terms of what I told, change in output current divided by reverse saturation current. Here you can see, and this IC is sensitive to each following parameters, like increase in temperature. VB decreases about, if VB decreases, because we are taking ideal values for all the type devices for silicon 0.7 volt. So but you have to see if there is a change in that value, so then stabilization will be not there. So already I told in the first slide, condition for stabilization. So VB should be constant, one condition I told. So if it is changing, then your stability will be also changing. And also reverse saturation current also changed, your stability will be changed. So these features already we have discussed. Now based upon this stability, you can calculate 3 stability factors. One is stability due to the leakage current, stability due to the base emitter voltage, and stability due to beta values. So anyone, because most popularly we are using this one, or in 3 of you can utilize it. So stability already I told, change in IC divided by leakage current, or change in IC with respect to change in base emitter voltage, or change in IC with respect to change in beta values. So these are the formulas are used to calculate stability in a circuit. So for example, if you see for emitter bias configuration, so this stability, if you calculate, this is an empirical equation. So change in IC0 is equal to beta plus 1 plus RB by RE divided by beta plus 1 plus RB by RE. So this equation, if you take, so here it is given for emitter bypass configuration based upon this approximation. Now for RB by RE is greater than beta plus 1 because RB is a very higher value you are considered. So RB is in terms of very much high value with respect to RE. So if it is very much greater than beta plus 1, so this equation will be, you can see, stability will be only beta 1 plus value. So here you can see RB by RE is greater than beta plus 1. So then this term will be 1. So then your stability will be only beta plus 1. If RB divided by RE is very much less than 1, so your stability will be only 1. So if you are plotting these values in a graph, so you can see this value, you can see if you are plotting the stability with respect to the resistance ratio values, RB by RE, so stability will behave like this. So stability, and this condition you can see for any circuit or any stability, you can see how resistance values are responsible for that. So accordingly, you have to take the resistance value. That does not mean you can take any value for your circuit. So this another important factor is stability, and from this graph you can see my circuit or my network should be in which region. So based upon that, you have to select your RB and RE values. Okay, so here you don't have to mug up the equation. So if you see most practical cases, RB plus RE is greater than beta plus 1. So at that time, stability will be beta plus 1. So if beta value is 100, then your stability factor will be 100 plus 1. So that's why you can see RB always we have considered this value. If I'm taking less than, stability will be only 1. Okay. So based upon this condition, this is followed. So in your circuit, or what example or question you can see, RB by RE always greater than 1. Okay, so you go for that. So similar approach you can follow for voltage divider configuration, stability, same equation. Earlier you have taken at RB, here it will be RTH. So only variation you can see RTH by RE if less than 1. So and stability, if you see earlier equation, in this equation, only variation is RB. Earlier you have taken RB, you are taking RTH. Because you already have seen this relation between emitter biasing configuration and voltage divider configuration. Only changes you have seen, this is if I'm considering the earlier cases, so this is your VCC and this is your RB. Now here we are representing in terms of RB, so that's why RTH. So in case of RB, you have written RTH. Other things are same, you can see. So for emitter bypass and this thing, as the standard you can take for better stability, RTH by RE should be greater than 1, beta plus 1. Okay, so the stability will be good. So stability will be, if you see, stability will be beta plus 1. So the relation you can see whenever you are selecting resistance value, you have to check. Am I audible to everyone? Hello?
Yes, sir, audible.
Okay. So this similarly for fixed bias configuration, if you see, because no RE is there. So in fixed bias configuration, RE is not there. So if RE is not there, so you can see stability will be only 1 because RE value is 0. So stability you can see it is 1. So that's why fixed bias configuration you have already I told it has poor stability. So that's why it is not popularly used. So poor stability and high sensitivity to various leakage current. So if you see in terms of stability, which configuration is considered, based upon you can select. Now what we have discussed, based upon that, one question is given here. For example, other questions you have seen, all values are there, but here you have to find out, design a fixed bias configuration. So design means already you may have the circuit, you have remembered what is the fixed bias configuration, but resistance values are not given. So you have to find out the resistance values. But earlier cases, what you are doing, ICQ and VCQ you are finding out. So in this question, ICQ and VCQ are given. You have to find out the resistance values. So same equation. In that equation, the only thing which data is given, which is not given. Accordingly, you have to find it out. So the solution already I have made it here. You can check it for your thing. So here you can see IBQ is equal to IC by beta, and IBQ is BCC minus BB by RB. So RB is equal to BCC minus BB by IB. So IB already given, because IB how to find out? Because IC by beta. ICQ is given, beta is given. So IB will find it out. From IB you can find out RB. Similarly, RC is output resistance. So you can use output equation BCC minus BC divided by IC minus ICRC is equal to 0. So earlier IC is equal to VCC minus BC by RC. So now RC you have to find it out. So IC will go to the denominator. So using this same formula, what you have derived, you can find out RB and RC value. Because this is a fixed bias configuration, so no RE is there. I hope this is clear, and look into carefully, then you can do similar type of problems also. It is mentioned in your book, given in your book. And here also for CB configuration, I have made this slide. You can go through that and you see for your thing. Whatever I told, same thing you can see input impedance is only RE value. But in case of common emitter configuration, which is beta RE. So this derivation we can already give it, you can see it. And output voltage gain and current gain, similarly you can see voltage gain is equal to here positive quantity, so which is equal to RL by RE. So what is the difference here? For example, you need a voltage gain with same phase, so you can use RL by RE. If I'm requiring a circuit where I need a voltage gain with out of phase, then I can go for common emitter configuration. So that's why you can see this will help you. But here you can see current gain will be very small, less. Alpha is current gain, so current gain will be very less. Clear? So current gain will be minus alpha. But current gain will be minus alpha means if I'm taking current waveform, it will be out of phase. Okay, is it clear to everyone? You can go through these slides once again, and it will give you the clear idea about common emitter configuration and common base configuration. Common base is not given in not in your syllabus, but whenever you are doing common emitter configuration, you can compare. Then it will be more easier to understand. And also common base configuration, one question is also given there. You can see it. So any queries anybody have, you can ask, because already time is over. So anybody has any doubt, you can ask. Otherwise, you can go through this presentation. Okay.
So can you share these notes?
Yes, yes. Every notes I'm sharing. Today also I'll share it. Okay. So if you other queries you have, you can ask. Otherwise, you can leave. Okay.
Thank you, sir.
Okay.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.